In this video, we should see the power amplifiers. So this is the first video on power amplifiers. We should see first the introduction of power amplifiers and class A power amplifiers. So introduction of power amplifiers. So usually power amplifiers are the last stage of a system. It deals with large signal. Therefore, the small signal models which we used in the earlier CS amplifier, differential amplifiers, CG amplifiers are not applicable for power amplifiers since it is dealing with large signals. In case of power amplifiers, linearity is very important. So linearity plays a major role in deciding what is the total harmonic distortion of the output waveform. So that's why the linearity of the power amplifier should be as linear as possible. And this power amplifier should have a low output impedance. This is required so that it can deliver maximum output voltage to the load. So it should have very low output impedance. Since these power amplifiers are placed at the last stage, so they will not be amplifying the signal. So the signal is already amplified, so we'll be dealing with a large signal. So what it should have is, it should have very low output impedance so that it can deliver maximum power to the load. Next, it should be designed to deliver required amount of power to the load in an efficient manner. Meaning, since this is the last stage which is driving the load, so it should be designed to deliver maximum amount of load to the maximum power to the load in an efficient manner. Meaning, the power amplifier should have very high efficiency. The output stage handles both low as well as high power. The power that can be that is handled by these power amplifiers will be low as well as high power. So power transistors are used if the power is more than 1 watt. So we know that for all amplifiers you need to have a transistor. If the operating power is more than 1 watt, we want to use power transistors in place of normal transistors. Now we should see the classification of the power amplifiers. They are classified based on the conduction angle of the transistor. So now here you can see we have 4 basic category of power amplifiers. One is class A. The conduction angle is 360 degree, meaning the transistor will be conducting for the entire cycle of the input signal. In class B type of power amplifiers, it will be conducting for only 1/2 cycle. In class AB, so it will be conducting slightly more than half cycle, but it will be far less than the complete cycle. Whereas class C amplifiers will conduct for a very small period, which is very small duration, which is less than 180 degrees. And this is based on the conduction angle. It will be either full cycle, half cycle, it is between half and the full, and it is less than half. So this is class A, class B, class AB and class C amplifiers. We should see how does the waveforms will look like. Now, as it was said that for class A amplifiers, the conduction is 360 degrees. Now you can see it is conducting the output waveform. The current is flowing in the entire full current is flowing through the entire cycle. Whereas in case of class B, as you can see here, this is class B, the current is flowing for only the half cycle, the another half it is off. Now this is class AB. As you can see now, the conduction angle is more than half. So this is half here, so another more than half. That's why it was said that for class AB, the conduction angle is more than 180 degrees, but it is less than 360 degrees. So this is class AB. So coming to class C, where the conduction angle is far less than 180 degrees. Now you can see 0 to pi is 180. Now it is conducting for less than 180 degrees. This is how we can classify different power amplifiers. So this is class A, class B, class AB, and this is class C amplifiers. Let us have a look at what is class A power amplifiers. Now this is a circuit diagram. I hope you can remember what is the circuit diagram. Now this is a CD amplifier. Now you can see there is the output is taken at this point, and this transistor to this transistor which is connected in the diode connected mode under resistance VDD2, and this M2 will going to form the current source. So which is acting like a current source. Now assume that the current of I is flowing here, and because of this applied input voltage, so there is a current I, a small I capital D1, so which is going to have both the small current, this is your AC current, not the small current, it is the AC current plus the DC current is the current going through M1, whereas the load will take only the AC current, the DC current is going through M2. So we can have a capacitor here also. This capacitor which is there from this to the load will block your DC current to flow there. You can have a capacitor here. So at the load we won't have only the AC component, and the DC component is going through M2. How do we find out the output voltage? The output voltage is nothing but, so as you can see here, so this is VGS1. So output voltage is nothing but input voltage minus VGS1. So since VGS1 is small compared to Vin, so we can almost think that the input to output voltage is almost close to input voltage. So what are the maximum voltage we can get here? Now we can see we have a plus VDD and minus VSS. Usually the voltages of plus VDD and minus VSS will be of the same magnitude. If it is 5, this will be minus 5. So the circuit is designed in such a way that, so under a normal condition, the voltage at this source, the output voltage is at 0 volt. So if it is 0, now to keep this M1 in saturation, we need to have a VDS sat. So what is the maximum voltage we can able to get at this V0? So V0 max is equal to VD minus the drop across this MOSFET when it is in saturation, that is VD minus VDS sat. Similarly, what is the minimum voltage of the output? It can be minus VCC, or it is now minus VSS plus of VDS sat. So it is this minus of this potential. Since it is negative, the V0 minimum can be minus of VSS plus of VDS sat, because there is a loss of voltage here. So that is this VDS sat 2. Assume that this is 5 volts. If it is 0.2, so this is minus 4.8, it will be 4.8. So output is going from 4.8 to minus 4.8. Now we should see, this is how the transfer characteristics of class A amplifier looks like. As you can see now, when the input voltage is 0, the output is negative, because as we see here, when the input voltage is 0, the output is minus VGS1. So, but in this graph it is written as VCC and VC sat. Now this is a transfer characteristics by considering the active device is a transistor, that is BJT. So this can also be very easily written as VD minus VDS sat 1. So this can be minus VSS plus VDS sat 2. So instead of VCE, you can have it as VDS sat. I can see this is like VGS. So this is the value of VGS. So if the voltage is more than VGS, so then it starts conducting here. Now you can see the slope is 1, meaning the output and the input are almost equal. So with a slope of 1. So this means to say that, so this linearity curve shows that the output voltage is following the input voltage. So for most of the region, so as long as the input voltage is within this, the output is not distorted. Now, as it was mentioned in the introduction, so we are supposed to find out what is the efficiency of this class A power amplifiers. So this is how the transfer characteristics of class A power amplifier looks like. So we should see how do we find the power conversion efficiency. So power conversion efficiency is given by the expression which is eta output power to input power. So here what is the output power? Output power is nothing but how much is the power that is delivered to the load. In this case it is a resistor RL. And the input power is nothing but the power that is done from the power supply. It is not the input power that we are feeding to the amplifier. It is not this input power. This is not this input power. We are talking about how much VDD and minus VSS. So the power due to this power supply, how much it is used to convert this into an output power. It is PAC, that is the AC power divided by the DC power. So that's what is the conversion efficiency here. The output power is AC power divided by the DC power. Input power is the supply power. If VDD magnitude is equal to the VSS magnitude, so as we know that output will swing from almost close to VDD to minus VSS, neglecting this VDS side. Now you can see this, you can write it as almost to VDD, this as minus VSS. So that's what is shown here. So this is output is swinging from VDD till minus VSS. So this is the output waveform. If we have a sine waveform, then how do we find the power related to this waveform? So power is given by Vrms square by RL. So we know that Vrms is nothing but V peak by root 2. So Vrms square, you can write it as Vp divided by root 2 whole square. This peak is nothing but the VDD. So we are replacing this peak by VDD. So it is now VDD by root 2 whole square. So we are retaining this RL as it is. Now what is the, so we can further write it as, so it is VDD square by 2RL. So this is what is the PAC, that is AC power delivered to the load, which is nothing but P load. We should also find what is the DC power that is drawn. So as you can see here, so since we have two voltage sources VDD and minus VSS, VSS has also the same magnitude as that of VDD. Actually the voltage is now 2 times VDD, the current flowing is I. Now since the voltage difference is 2 VDD and the current flowing is I, the power that is drawn from this supply source is 2 VDD into I. So that's what is shown here. Since there are two power supply voltages plus VDD and minus VSS, the bias current is I. The power supply power is PS, which is nothing but the DC power, which is nothing but the overall voltage multiplied by the current. So it is VDD plus VSS into I. The magnitudes are same, then we end up with 2 VDD into I. So by looking into the efficiency equation, so it is nothing but power delivered to the load given by the supply power. So upon substituting that for PL and PSS, for PS, so we have VDD by 4RL into I. We know that the output power, whatever your output voltage that we are getting, this is VDD. So this is actually that is being developed across the resistor RL. So this is what is RL. So whatever V0 we are getting is the voltage of across RL. As the current flowing through this changes, the V0 changes, because ID1 into RL is V0. So as you can see here, so this is the output voltage is nothing but output voltage cannot be more than VDD. So that output voltage maximum can be RL into I is nothing but VDD. So we can substitute this RL into I as equal to VDD, then this VDD and this VDD will go off. So we left out with efficiency equal to 1 by 4. That is, the efficiency is only 0.25, which corresponds to 25%, meaning a class A amplifier has a very poor power conversion efficiency. That is, if it has to deliver 1 watt of power to an output, it actually needs 4 watts of DC power. So meaning, for a resistor, if you want to deliver 1 watt of power, from the power supply we are supposed to consume 4 watts of power, which is a very poor performance. Meaning, a class A power amplifiers are rarely used for high power applications due to their poor power conversion efficiency. Even though the ideal conversion efficiency is written as 25%, this is the ideal case. Typically, the efficiency is the order of 10 to 20%. So that's why at higher powers, this class A power amplifiers are not used. So it will be used for only powers less than 1 watt. So this is how we can find out what is the circuit diagram for the class A amplifiers, where it conducts for the entire cycle. And now you can see this is conducting for the entire cycle, and we have the output voltage conducting for the entire cycle, and we found that the efficiency is given by output power by input power. Output power is the power of the sine waveform, which is nothing but RMS square by RL, voltage RMS square by RL. We also find the PDC, that is nothing but the power supply power, which is nothing but 2 VDD into I. So from this we found that efficiency is hardly 95%, which is a poor performance.